This morning, good morning, is Richard James, and he's right over here. Okay.
Thank you, Randy. I guess I need a...
Oh, we should have done that ahead of time. I won't. This won't.
okay.
This won't count towards your time.
Okay.
Can you identify your tartan while you're hooking up?
I cannot. I'm sorry about that for the Scots in the audience. But I can identify a little bit what I'll say about some new materials that were discovered in a kind of, I would say, a kind of essential way by using mathematical ideas. And many people contributed. And this is a very short list of the people that contributed most to the talk I'm presenting, but there are also many people I notice in this audience that made major contributions to this area. And these materials are materials that undergo phase transformations, crystalline materials that undergo phase transformations. So quite different from yesterday, and I'll try to contrast that a bit. And as I say, it's about the reversibility of phase transformations. And so I thought I would start with an example of a material which is highly non-reversible. So this is the phase transformation, alpha to beta phase transformation in the pure element tin. So if you cool tin to minus 15C, you get a highly non-reversible phase transformation. So this is to give you the idea that not every phase transformation is nice and reversible, go back and forth many, many times. With tin, you get a pile of powder, and if you want to return it to its original shape, you have to melt it again and recast it. So, you can read a textbook reason why this tin is not reversible. The textbook reason is it has a big volume change, and therefore, for some reason, due to this volume change, it's not reversible. We'll come back to that point. So these are the kinds of phase transformations I'll look at. Are these phase transformations in crystals? They have different names. I'll use a traditional terminology, which is a martensitic phase transformation. This is the most simple one, where you have, in this case, FCC phase. It may be an alloy. And it undergoes, at a critical temperature, so this is a kind of temperature axis, it undergoes a distortion. This would be called a cubic to tetragonal phase transformation. The terminology for this phase would be martensite. This phase is austenite. And these are the so-called variants of martensite, the three variants of martensite in this case. And you can measure reversibility in many ways. One way I'll measure it is by going back and forth through the phase transformation and measuring a property and see if it degrades. Another way which is quite relevant to many applications is hysteresis. And that's pictured here. And this is a case in which hysteresis can be seen in the passage from one variant to another of martensite. That's in this case. This is an experiment in which I'll show you I may show you that, I'm not sure, the setup of this experiment. But in any case, it was stress-induced phase transformation. This is the difference, and biaxial, this is the difference of the stress on the two axes. And you see that it has a hysteresis loop. So it begins to transform here, and it transforms back here. Of course, the main thing of interest here will be the transformation from the austenite phase to the martensite phase. All three variants then would be in the low temperature phase. And then you would also get a hysteresis loop. This is the percent of martensite versus temperature. You begin to transform here, you finish here, and so forth back. Usually people in material science, they fit this by a parallelogram, and they take the half width of the parallelogram to measure the hysteresis. Let me come back just to that stress hysteresis case. So I'm looking at this case right here, and in fact that was done with a biaxial testing machine. That's why the sigma 1 and sigma 2, those are the stresses on the two axes, and the microstructures during transformation look like this. In fact, this was a dead load biaxial testing machine, which had a special property that that homogeneous deformations are stable states in this machine. So it passed from one homogeneous deformation to another homogeneous deformation by applying the loads. But in any case, what I want to illustrate is not that. What I want to illustrate is the fact that, that here's the hysteresis loop. And this was done by testing, by periodic stress as a function of time. And this is the period of the stress. So it goes from 10 seconds to 1,000 seconds. And you can see here that the loop, despite the 2 order of magnitude change in the rate, the loop is very nearly the same. So that's rate-independent hysteresis. And that's the kind that's most interesting in the case of phase transformations. So this is stress hysteresis. I could also have done similar experiment with in this case, thermal hysteresis. I would see a small rate effect there. And in fact, it's understood. It has to do with the fact of getting the latent heat in and out of the piece of material. But the main part of the hysteresis, the main point is that there's a part of the hysteresis, which is the main part, in which if you go around the hysteresis loop slower and slower and slower, it does not collapse to zero. So if you're a mathematician and you're used to modeling things by some, when you have some dissipation, you use some rate laws or some viscosity or some viscoelasticity. That's wrong. That would be the wrong model because it would not have this property of rate-independent hysteresis. The hysteresis loop would collapse to zero if you went slower and slower around the loop. So there's lots of ideas you can see in textbooks about what causes hysteresis. So one of the most popular ideas is it has to do with pinning of interfaces by defects. That non-transforming parts of the material, an interface between the phases hits a non-transforming part, it gets kind of stuck there. It requires an additional, say, lowering of the temperature to make this interface break through the defect and pass further. This happens both ways through the phase transformations. This is one idea about hysteresis. Another idea, which certainly is relevant to the materials that were discussed yesterday, it has to do with thermal activation. I like to explain that this way. So I'm drawing here the potential energy of the system. So this is potential energy as a function of all the degrees of the freedom of the system. And if you thought atomistically, there's many, many huge number of degrees of freedom. And no one knows, of course, what this surface looks like. But on the other hand, there's some thoughts about what its qualitative features are. And so the main thought is that it's thought that the Martensite phase has very steep energy wells in the potential energy versus all the atomic degrees of freedom. So there's these sharp wells down here. Of course, the state of the system is represented by a dot on this surface. And this dot is, of course, moving around because its motion is governed by the equations of molecular dynamics. And so this other idea about hysteresis is that the system might be parameterized by temperature, and that would be set by the initial conditions of the MD simulation. And so one idea is that this system is in this Martensite phase. You raise the temperature, and eventually it passes out and it transforms to the austenite phase here. In fact, it's the average position of this dot may actually be on the top of one of these. This surface is thought to be very wiggly, and it might be on the top of one of the little mountains on this surface. That would be called entropically stabilized austenite. And then it sits there on the system. Now you cool the system, and you can tell by this picture it's probably true that it's very hard for the system to find its way back into these energy wells than it is to get out of the energy wells originally, and therefore there's hysteresis. In other words, if I'm doing the experiment at finite rate, there would be sort of two different temperatures at which the system leaves the well and comes back into the well. And that's, I think that's an appealing picture also from a mathematical point of view. So the origins of hysteresis and reversibility that I'll speak about are completely unrelated to these basic textbook ideas. So as a third idea, that's the main subject of my lecture. Okay, so to explain that idea, I need to introduce some basic things. The first is that when we have this phase transformation, there's a transformation stretch matrix or transformation matrix. It's the linear transformation which takes the austenite phase to one of the variants of the Martensite phase. Of course, for the other variants, there would be similar matrices. And those matrices are expressed in terms of some numbers, the so-called lattice parameters, and in fact, the matrix is written here. The eigenvalues of that matrix are in fact alpha, beta, and gamma. But I need, for my talk, the ordered eigenvalues, so I'll call them lambda 1, lambda 2, and lambda 3. And in particular, the middle eigenvalue of this matrix is going to play a big role in my talk. Okay, so in reality, the crystals are not so simple, and most of the crystals we deal with actually don't consist of a single Bravais lattice, which is this case, but they consist of many Bravais lattices. In this case, I've drawn 3 Bravais lattices. It turns out that each one, when you have one of these phase transformation, undergoes the same linear transformation. If you didn't have that, you would destroy periodicity. So, and in that case, that's the transformation stretch matrix I'm going to use. In fact, one of the materials that I'll show at the end of the talk has 18 of these Bravais lattices. That's not unusual, that we have many interpenetrating Bravais lattices to describe the crystal structure of the materials. Okay, so I need a basic theory to describe what I'll do, and it's a variational theory. There's a free energy density phi, which depends on deformation gradient and temperature. I guess this is kind of familiar to people. It has energy wells. They're defined by the transformation stretch matrices. I picked out this copper, aluminum, nickel alloy just as an example. It has 6 variants of Martensite. They're symmetry related. There's a symmetry theory that I'm not describing. I guess one could guess how that could work out. In any case, the way you have to picture this phi is you fix the temperature. So I'm at the transformation temperature now, and you imagine a phi axis coming out at you like this, and the energy surface is a function of deformation gradient. So deformation gradient is a 3x3 matrix. So this square is all 3x3 matrices. And there's this phi axis coming out, and the temperature is fixed. And now this energy surface it's minima, so it comes down and touches the screen at some circles. And the circles are, this is at the transformation temperature. First of all, it touches the screen at the identity. The identity is a minimizer of phi at theta c. And there's also rotational invariance, so that's what the circle denotes. So if U2 in fact is also a minimizer, equi-minimizer with the identity of phi, and the circle just represents all rotation matrices times U2. So it's a kind of copy of SO3. It's SO3 times U2. And this is SO3 times U1, this is SO3, and so forth and so on. In this case, there's 6 of these Martensite energy wells, and this is the austenite energy well. Everything's at the same height because we're at the transformation temperature. If we raise the temperature, these wells go up relative to this one. If we lower the temperature, these wells go down relative to this one. Typical first order phase transformation picture. And we know the positions of those wells very accurately because we get these numbers from X-ray measurements. So we know the positions of the wells. I mean, so from a practical viewpoint, the further you go away from the wells, the kind of less we know. But we know the symmetry very well. So anyway, the explanation I'm going to give rests on this picture in some sense. So this is surprisingly generic. This is the generic picture, at least in a kind of semi-reversible Martensite material, of what we see at the finest scale. The microstructure can be very complicated, but if we focus at the finest scale, and we look at a place where both phases are present, we'll see this. This was taken in a single crystal. It's quite macroscopic picture. But anyway, it's this sort of picture we would see. And this is the austenite. And these are two variants of the martensite. And the reason, I'm going to tell you why there are two variants, or why they're not just a single variant, and many things about this picture. In fact, this picture, my explanations rest on this picture. Roughly speaking, to begin, you could imagine there would be a single variant of martensite over here. But if you work that out, there's a shape change. So in going from austenite to martensite, there's a shape change. And if I tried to put a single variant over here, even if I allowed it to rotate around, I would have an enormous stressed transition layer in there that's highly disfavored by energy minimization. So in fact, this microstructure has to do with energy minimization. So the way it goes is the following. Remember, these matrices, these transformation stretch matrices, define the energy wells. So first focus on these bands on the left, which are pictured up there. And it goes like this. So if we're going to do energy minimization by hand. So we should pick two states from the energy wells. So I'm going to pick U1 and RU2. Of course, these cannot be the gradient of a continuous function unless there's some compatibility condition. So it all rests on compatibility conditions. And in fact, it's also we have rotational invariance, so we can pre-multiply by the same rotation. And then the picture looks like this. And in fact, so the condition of compatibility then assures the picture does look like this and not two separate blocks is this condition. So that's an algebraic condition. The difference, this U2 and U1 are given. R is a free rotation matrix. Algebraic problem. Find R such that RU2 minus U1 is a rank 1 tensor, A tensor N. So if you do that, that's not hard to do. And there's two solutions, explicit solutions. You write down everything about those three quantities. If you come back up here and compare with this one, if you've chosen the variance correctly, you'll accurately produce this picture, even at atomic level. Okay, so that's fine so I've discussed so far just the left part here, but now we have this part right here, and I'll discuss that. So I take and I make a laminate of those two variants. I allow myself a volume fraction F, and I allow myself a 1 over K here to make this finer and finer. And I put the austenite here, and I allow that to have a rotation matrix there. And it turns out that because of the reasons I said earlier, that a single variant is not compatible with the austenite, but you can put a layer, a stressed transition layer in here. And you can show the following. You can show that if you orient this interface just right, and you choose this F just right, then you can drive the energy in this transition layer to 0 by making K go to infinity. Okay, so that's a minimizing sequence for the energy. But it requires special conditions. As I say, you have to get these things exactly right. And there's quite rigid calculation. You get 4 normals to this interface. There are 2 possible Fs. I'll tell you a bit more about the calculation later. But it's fairly rigid. And if you take, among the several cases you get where this is possible, you take one of those cases, it will agree incredibly well with this picture. Okay? It does not agree with the picture in one aspect. And then you have to look very closely at this picture. Maybe I'll first point it out here. If the picture's bigger, you can see it. Is actually there's branching of the interfaces as you go toward the interface, this interface. So there are more bands here than there are here. I can tell you a little bit about that, but first let me show you I want to show you 2 things by this movie. One, of the fact I want to show the branching, so you'll be able to see this branching. The second thing is, this is a single crystal, and it was detwinned. It's in the martensite phase. Okay, so this is one variant of martensite. In fact, it wasn't completely D-twins because there's some other variants hanging around here. But anyway, mostly one variant of martensite. And it's being heated from the top. So it wants to transform to austenite. And a remarkable thing happens. So it's, it's going to austenite. Austenite is a single phase. There's no variance. But when it goes to austenite, it creates microstructure in the martensite. It creates microstructure in the disappearing phase. Okay? So here's what microstructure it creates. Oops. Wow, it's hard to see that. Is that? Okay, there it is. Okay, so it created a two-variant microstructure, in fact, exactly the interface I showed you. And if you look carefully, I'll speak quickly, you'll see that there's also branching of those boundaries there. So let me say a little bit about the branching, because that modifies slightly the explanation. And it's been studied a lot. It looks like this. This is a very partial list of people who have worked on this. And so let me just say something about that. There was seminal work by Bob Cohn and Stefan Müller about this based on this model, and they gave a scaling argument which rigorously shows that there's a scaling in terms of epsilon is, you could call it this is an interfacial energy term. So this now adds interfacial energy to the previous model. Okay, but it's also very simplified, and there's an elastic energy term. And there's also a constraint which models the fact that there are energy wells. Anyway, if you study, or these guys, when they studied this energy, they proved that it has an upper bound which goes as epsilon to the 1/3, L to the 2/3, where L is the length of the martensite plate. So the length of the martensite plate plays a big role. Now, the construction I did with the minimizing sequence, if I just added interfacial energy on the bands, I would get a different scaling law. That's the classic scaling law. That's this one. And you can see this law is, this energy is smaller than this energy, at least asymptotically, if L is large or and epsilon is fixed, say, or epsilon is small and L is fixed. Okay, so you expect this branching when the martensite plate is sufficiently large. But there's actually a little defect with this energy. It only penalizes jumps in the y direction, and so actually the interfaces could potentially turn up as you approach this interface. And in fact, they do in this model. Okay, so it wasn't realized, I think, originally, but it was realized implicitly by Conti and Chan. And we've taken a look at this recently, and we use a model which is the same phi as I used earlier, and we make it as far as we know accurate, and we use this model for interfacial energy, sharp interface model like this. And anyway, to make a long story short, this branching construction works quite well, and we're able to evaluate everything using this copper, aluminum, nickel alloy that I've been showing all along. And with a length of the martensite plate of 0.5 millimeter and epsilon, this is an interfacial energy constant. This is the material constant we know the least about. But it's a very reasonable value. You can get a very nice agreement between the branching construction and the actual microstructure with the right number of right generations and so forth as you approach the austenite-martensite interface. The effect of this branching is quite, in some sense, dramatic. In the naive construction that I did, all the energy is in this transition layer, and there's no elastic energy back here. In this model, with branching, the elastic energy is diffused. It's quite diffuse, so it delocalizes the elastic energy away from the interface, and it adds interfacial energy. So in some sense, this provides a potential reason for hysteresis. Okay, so that's the one I want to explore. Just this calculation. So you imagine that the specimen is all austenite, all red. And now you're at high temperature, and now you're cooling the crystal. You reach a point where the energy well of the martensite is lower. Okay, so it wants to transform to martensite if you're doing energy minimization. But if a little bit of martensite formed in the material, it would also have to accept the interfacial energy, which by either model, the interfacial energy on these bands together with the elastic energy, which are positive sources of energy. So then you would say, okay, that should create an energy barrier. So I should have to lower the temperature more to compensate for the positive sources of energy that are in this picture. Okay? So you can study that mathematically. We did study that mathematically. But there's also a very easy, well, not so easy, but very obvious experimental thing to do. And that's what we did. It's based on this lemma, is that remember this transformation stretch matrix with its 3 eigenvalues, the middle eigenvalue being 1 is necessary and sufficient that this equation is satisfied. That's the compatibility condition between pure austenite and a single variant of martensite. So, and in effect, there are 2 solutions. If lambda 2 is 1, there are 2 solutions. Those are in the 2 rotation matrices. Those are the 2 solutions. So there's a perfect interface between austenite and martensite if lambda 2 is 1. And now that's lambda 2 is the middle eigenvalue of this matrix. And this matrix has these lattice parameters. These lattice parameters, as you change the composition, they depend on the composition of the material. So these are alloys. So you're allowed to change composition, and to still the theory makes sense, and it has the effect of changing the eigenvalues of this matrix. So you can start with a material with lambda 2 close to 1, and you can keep changing composition and try to make it exactly 1. Okay? So that's what we did. We did it first in my lab. We saw a very dramatic drop. And then it was people who do combinatorial synthesis, in particular Alfred Ludwig and Ichiro Takeuchi, were attracted by these kind of results. They realized that combinatorial synthesis was an ideal tool to study this, and they made many, many specimens. So each one of these markers is a specimen. And they drove the hysteresis to near 0 by tuning the material to make lambda 2 equals 1. And here's a close-up of the region near 0. So, of course, so each dot has a different composition, but what I've done is replotted the data versus the middle eigenvalue, not versus composition. So I've plotted the width of the hysteresis loop versus lambda 2. Some of these are near 0 hysteresis. Of course, those combi methods are not so accurate. So the measurement of hysteresis is one has to be careful about those calling it exactly 0 or exactly 1 or something like that, but it's certainly very small. So you may say, so from a mathematical point of view, it looks like a singularity. And this is a reason why, so you should keep in mind that these nickel titanium X alloys, they were studied a lot. They're probably the most studied phase transformation of all phase transformations, maybe outside of steel. These days it's the most, but in the old days it was still studied a lot. So people made many thousands of these alloys before these results. So why did they miss the singularity? The point is this is very sensitive to composition. So when they made their alloy series, they always jumped over the compositions where lambda 2 is 1. So that's why you need mathematics. Okay, so this is an alloy. In fact, we used to think this was the lambda 2 equals 1 alloy, but it's quite close to lambda 2 equals 1. Actually, 9.25 is much closer to lambda 2 equals 1. But anyway, PD 11 was once thought to be. And with Nick Schrijvers in Belgium, in Antwerp, we did, or he did, high-resolution transmission electron microscopy. And you can see many of these lambda 2 equals 1 interfaces. It turns out that n in this, if you calculate the n and the a and the q, n is in fact 7 minus 5, and that's the measured normal to this interface, and the angle of rotation agrees with the angle in q, and so forth and so on. Okay, so now you can think, well, okay, maybe this, what is it? It's all about conditions of compatibility between the phases. So you could think maybe there's even stronger conditions of compatibility between the phases besides lambda 2 equals 1. And there are, and I want to describe, we call them the cofactor conditions, and I'll describe them now. So again, now we realize maybe the principle is this compatibility is the important thing. So I already described the solution for these bands. You solve this twinning equation. I described this reducing the energy in this transition layer to 0 by refining the twins. That gives rise to a second equation, which I didn't write down. That's the compatibility condition that allows you to drive the energy to 0. And it's also, this is also the equation you would get in a similar way if you use the branching construction as well. So it's in both cases. So I want to tell you about a little bit the solution. So in this case, we already discussed this. We found the R, the A, and the N, and there were two cases, and I now assume that's done. So we know that the A and the N and the R, and now this is another free rotation matrix. The F is a free variable. That's the volume fraction here of one variant versus the other, and B and M are free, so we're solving for those. So if you're solving for the basically R hat, F, B, and M, you might want to eliminate the R hat by taking the transpose of the equation times itself, and that gives you a function GF. And it's known that it's again a middle eigenvalue condition. It's known that a matrix, a symmetric matrix, which this is, has this form if and only if its middle eigenvalue is 1. So again, we have a middle eigenvalue. So we have to choose, but now we have a free variable, the volume fraction f. So the goal is choose f so the middle eigenvalue of GF is 1, and we drive the energy of this to 0, assuming no interfacial energy. Crystallographic theory of Magnetoelectric. So if you want to decide whether a matrix has its middle eigenvalue equal to 1, well, you could subtract the identity and take the determinant. That's certainly a necessary condition. Maybe it will give you an eigenvalue which is not the middle one, but anyway, you can start here. And this looks like a 6th order polynomial, but it's actually quadratic and symmetric about a half. So this looks like that. It's a quadratic function which is symmetric about a half. So to get started, we should look at that function. And you can plot this for various phase transformations. Everything is measured in this at this level. It's just lattice parameters, really, symmetries and lattice parameters. And if you take a typical steel, some of the steels actually have roots, so they would satisfy this, but other ones do not, and those would all be non-reversible martensites. This material, for example, has a quadratic function which looks like this. There's an f star, 1 minus f star. That f star, with or without branching, agrees very well with the local volume fraction. And I neglected the fact that the eigenvalue you get from one of these roots, it has to be the middle one, and that gives you an inequality. If you satisfy that inequality, there are 4 solutions, it turns out, 2 for f star and 2 for 1 minus f star. They look like this. If you take one of those solutions, it will agree very nicely with this picture. Now we discussed the case lambda 2 equals 1. What happens to this parabola when lambda 2 equals 1? Well, of course, when lambda 2 equals 1, the end states are roots. And so the parabola looks, in fact, like this, and generically like this, and you get the 4 solutions of the crystallographic theory, the perfect interfaces between austenite and martensite. But now you can make the obvious extrapolation here. So what you would really like is a material in which this quadratic function is identically 0. Okay? Why not? And then, of course, we have to worry a little bit because we have to make sure that for all values of this f, then there's an inequality. Okay, it turns out that we're always getting the middle eigenvalue, which is the one being 1. So you can reduce this to algebra. It's to make the endpoints as roots. It's the old middle eigenvalue condition. And it's a quadratic function, so you make the derivative at the end 0, that's this condition. And this is the inequality that makes sure that you're getting the middle eigenvalue is the one that's vanishing. So, okay, so can real materials, so this would be quite striking because you can vary the volume fraction continuously from 0 to 1, and in every case you have a low energy interface. And real materials can satisfy these conditions. So first of all, look at them theoretically. So this, I'm varying the volume fraction from 0 to 1, and in every case, you can reduce the energy in the transition layer to 0 by refining the twins. So you can see that adds, you certainly have the cases 0 and 1, which correspond because this lambda 2 equals 1, but you also have many intermediate cases. It depends on the solutions depend on the twin system, and I won't go into the details, but if you're familiar with compound twins, type 2 twins, with type 2 twins, actually it turns out the twin boundaries are parallel to the austenite-martensite interface. So you don't need any transition layer in these cases. These are 0 elastic energy cases. For type 1 twins, there also, half the solutions have the property that there's, again, no transition layer. So this is very interesting. If you satisfy these cofactor conditions, each one of these regions has a big strain in it, or may have a big strain in it, and everything is fitting together perfectly, and there's no stress. Okay? And you can vary the volume fraction from 0 to 1. And you can, this is part of Sherry Chen's thesis, actually. You can make curved austenite-martensite interfaces. You can vary volume fractions. You can have nucleation mechanisms where martensite nucleates on the corner of a cube, or austenite nucleates on a martensite twin band. So these are two variants of martensite and austenites. All these pictures, there's no elastic energy. There's many possible arrangements. There's a more complex arrangement with 4 variants of martensite. Every region has large shape changes. Everything's fitting together perfectly. No stress. So that seems to be a quite interesting thing to try to do. I'm going to have to look at the time. So, okay, the time is looking good.
I'm going to stand up when you have 40 minutes left. When you have 5 minutes left.
5 minutes left. Okay, great. So you have a lot of time. Okay, so again, it's some algebraic conditions. So you look for materials. You try to change composition to find materials that satisfy these conditions. It's more difficult than just satisfying lambda 2 equals 1. The natural way to proceed is you first find a material which satisfies lambda 2 equals 1, or you tune it to satisfy lambda 2 equals 1, and then you work on this second condition. And you need some compositional variables to try. There's good starting points, and I'm not telling you all the good starting points, but there's some good starting points. These are materials which have lambda 2 equals 1, or very nearly equal to 1 already. And if you check, everything's measured about these materials. This is a good starting point. There's a gold, copper, zinc alloy. That's a good starting point. And actually, VO2 is a good starting point. So 5 minutes from, not from the hour, 5 minutes from quarter of. Okay, then we have to go a little bit faster. Because you want to leave time for questions. Okay, so we tuned.
5-minute talk.
Okay. So we tuned this alloy to satisfy lambda 2 equals 1. And it turned out that it's zinc 45, gold 30, copper 25. In this particular measurement this is calorimetry, it's measured to have 0.2 degrees C hysteresis, which for a big first order phase transformation is very, very unusual. I'll tell you something qualitative about that. Don't worry, you'll get your 5 minutes. Is when in these Martin-Siddick phase transformation, there's an interesting phenomena where if you transform once, this is the acoustic emission, they emit sound, and then you go back and you transform again, you get very nearly the same microstructure and very nearly the same, even acoustic emission, even the tiny peaks in acoustic emission can be identified from one cycle to another. That's generic in Martensites, and I guess I won't show the movie. There's also a movie here which shows this reproducibility, but in the interest of time, I won't show it. But anyway, that's a generic thing. So now I want to show you what cycling looks like in yeah, there we go. So what cycling looks like in this gold, copper, zinc alloy that satisfies the cofactor conditions. So you can see it's quite unusual. Every picture is different. There are many things about all these pictures which are very unusual. They're curved interfaces. There are unusual complex microstructures. So I think we'll hear something more about this in later talks. But there's quite unusual. Another thing about this is that Francisco Della Porta, I guess, may speak about later, is that when the interface passes by, there's right behind the interface, there's very little relaxation. The microstructure is set already behind the interface. But that's a very strong restriction on microstructure, because it has to be, every point has to be compatible with the austenite in some previous moment. Okay, we can stop very near the end now. This is a pillar compression experiment. So this is stress-induced transformation, which is more demanding than just measuring the hysteresis. And so this is the zinc gold copper alloy. And you can see cycle 1 is here, is in blue, and cycle 100,000 is here. This is each cycle 6% strain. Peak stress is 600 megapascals. So that's a lot of stress on each cycle. So that's quite surprising, especially in view of the fact that it's a zinc gold copper material. We also did some theory about that. So the second alloy, I think you'll hear more about from Eckhard Quandt. It's this is the other known alloy which satisfies the cofactor conditions. It's a titanium complex alloy, titanium, nickel, copper, cobalt. And I'll just maybe remark that this is cycle 1, and on top of that is cycle 10 million. And this is, again, very high stress, 400 megapascals. If you're a mathematician and you don't know megapascals, the yield stress, the failure stress of the steel that holds up this building is maybe 200 or 300 megapascals. So, and this is 10 million cycles. So that's quite surprising. So thank you very much. Yeah.
Question? Go ahead.
When you discussed the branching,
Yeah.
you had an image of various length scales.
Yeah. So
As the number of branches increased, it seemed the length scale decreased.
yes, that's right. There's a particular scaling law for the. It's self-similar. It's a self-similar scaling as you go toward the interface.
So what's its fractal ordering? Do you know?
I mean, it's not a fractal. It's got a. Yeah. I mean, it's just simply self-similar layerings. Each one is a dilatation of the neighboring one, and it's shorter. So that's all. Yeah. Yeah.
If you have a material which satisfies lambda 2 equal to 1, and now you want to get closer to the cofactor condition, how do you guarantee that not lambda 2 equal to 1 is spoiled if you change again the composition?
Yeah, it will be spoiled.
So there's no mathematical.
No, it's. I mean, one can try to define the surface. So there are two. Say there in the cubic to orthorhombic case would be 3 lattice parameters. In the cubic to monoclinic case, 4 lattice parameters, and So in the space of 4 dimensions or 3 dimensions, there's a surface on which these conditions are satisfied. And the only thing we try to do is define that surface, you know, and by some, and it's not, you don't need any sophisticated mathematics for that. It's just defining a surface by some measurements. And yeah, you're right. One has to be, could be optimum ways to do that. Yeah.
Is there a way of interpreting the algebraic conditions that you get in terms of closeness metric in matrix space, things like that?
It's a lot like the cofactor conditions are in structural mechanics. You have like trusses, and they're, you know, so there's all these bars and they're joined together, and then if you make the bars just the right length and you put the nodes in just the right place, the truss has a mechanism where it collapses, right? And it can be rigid, but with special choices it collapses. It's very much like that. Mathematically, it's infinite dimensional, but it's very much that sort of thing, that there's just some special conditions under which there's a mechanism, let's say. Yeah. So I don't know if that answers the question, but that's, yeah.
No, I think we should move on. We should thank Rick again. And